All right, so Chapter 8, Bonding, Part 1. So in Chapter 8, we'll start with the basics of bonding, cover how do we show bonding, the differences between ionic and covalent bonding, and then drawing out the structure of molecules in a simple format, while in Chapter 9, we'll go more into the theories behind bonding, making it three-dimensional, the reasons behind why things bond, and being able to explain larger, more complicated structures and bond angles and that sort of thing. So this is the basic concepts of bonding. So the first thing we're going to talk about is the idea of Lewis dot structures. So if you took a high school level chemistry, this stuff is probably going to be a little bit of review. So in Chapter 7, we reviewed for a main group element how to determine how many valence electrons are in that atom. So how do you tell for a main group element?
Right there. How many electrons are in the atom?
How many valence electrons?
What group it's in?
What group number it's in. Good. So anything in group 4 has 4 valence electrons. So if I'm looking at group 4, I've got carbon, silicon, germanium. These things have 4 valence electrons. The reason why the valence electrons are so important is because they're on the outermost shell. They're the ones that aren't involved in bonding. We also talked about how in Chapter 7, things, when they become ions, want to gain or lose electrons to look like what family? Noble gases. Everything's going to want to gain or lose electrons to look like noble gases, but they can also bond and share electrons to look like noble gases, to become isoelectronic with noble gases. So we're going to show these, first of all, using atoms and a Lewis dot structure that's just going to show how many valence electrons are there. So a Lewis dot symbol is the element's symbol, which is just its symbol from the periodic table. Hydrogen is H, helium is He, etc., surrounded by dots that represent how many valence electrons are there. So this table is on page 327, and it shows for the main group elements what their Lewis dot symbols look like. So group 1A, so hydrogen, helium, sodium, etc., has 1 dot. Group 2 has 2 dots. Now, we know that electrons repel each other, so when we are drawing out these dots, we are going to spread them out. It doesn't really matter which side you start with, but then the second electron would be on the opposite side. So when we're looking at beryllium here, beryllium has 2 valence electrons, so it would have 1 on each side. When we get over here to nitrogen, we have 5 valence electrons. At that point in time, we have to start pairing up. Now, just like when we were doing the orbital diagrams, you have to have 1 electron in each orbital before you start pairing up. Here, same deal. You have to have 1 electron per side before you start pairing up. And what's the maximum number of valence electrons you can have? 8. So our noble gases have 8 valence electrons, 2 per side.
What about helium?
Well, yes, helium's maximum is only 2.
Also, it's paired up already.
Yes, helium shows them paired up because in the helium atom, they're both in the 1s, and that's a stable configuration for it. It doesn't bond, it's inert, so with helium, you just show them 2 on one side. So when we go to add or remove electrons to make ions, that's going to change that electron configuration. So on a test question, I'm more likely to ask you, what is the Lewis dot structure for an ion than for an atom, because, hey, I just gave you a table that shows you all of the atoms. So you're going to add or remove electrons appropriately and then show the charge. So let's try this out. Let's draw the Lewis dot structure for the fluoride ion. So just like when we were writing the electron configurations for ions, we start with the electron configuration for the atom and then added or removed electrons. Same thing here. We're going to start with the Lewis dot structure for the atom and then add or remove electrons. So fluoride, we start with fluorine. Fluorine would have how many dots around it before it becomes an ion? 7. So I'm going to start with 1 per side, 1, 2, 3, 4, and then start doubling up. 5, 6, 7. Again, doesn't really matter which side I leave out. Now to become fluoride minus, am I going to add an electron or remove one? Add 1. So I'm going to add 1 more, so now it has a total of how many? 8. So the last step is to show the charge. Rather than just putting a negative charge right here I'm going to put this in brackets first. The reason why we have to put brackets is because this negative charge floating out there, you don't know if that's talking about a negative charge on the entire atom here or a negative charge just on one of the electrons floating around. So I'm going to put brackets around you to show that it's a negative charge on the entire atom, not just one of those electrons is negative. Well, they're all negative, but. So with negative ions, you add electrons. Typically, they're going to add so that you get 8 valence electrons because they're all trying to be isoelectronic with the noble gases. And then you put the brackets around it and the negative charge on the outside. Questions about that one? All right, potassium. So potassium normally has how many electrons? 1. Doesn't really matter which side we put it on. 1 electron. Now to become potassium plus, am I going to add or remove an electron? Remove. So let's say eraser and remove an electron. And then put a positive charge. Now the reason we don't need to put brackets around this is because the only thing there is the potassium. You don't see any electrons, so there's no confusion about is the positive charge on an electron or on the atom because the only thing shown there is the atom. You do not go down to the next shell and say, okay, now you've got 8 valence electrons. That's not what we're trying to get at. We're saying from the original shell we have no more electrons left. So the Lewis dot structure for potassium plus would show no electrons because its original shell is now empty. All right, so go ahead and try the sulfide ion, S2 minus. On your own. So once we become sulfide, how many dots will be around it?
6.
Start with 6, but once it becomes sulfide, it becomes 8. 1, 2, 3, 4, 5, 6, 7, 8. What else do I need?
-2 with
Brackets and 2 minus. So there we go. And that is section 1 for chapter 8. Super hard. Ah, so overwhelming. All right, ready to move on to section 2, ionic bonding? All right, so ionic bonding. So we should be familiar with at least the idea of an ionic bonding occurring between ions, and they're held together by electrostatic charge that we learned about back in chapter 5, the attractive properties of the positive ion and the negative ion. Now we're going to quantify that using the lattice energy. So ionic bonding refers to that attractive force between ions that holds them together. So they have to be oppositely charged ions. That's way back in chapter 2 when we were first learning about making ionic compounds. We would have a positive ion, which was either a metal cation or NH4 plus ammonium, and a negative anion, which was either a non-metal with a negative charge, or it was a polyatomic anion with a negative charge. So let's talk about the process that goes about making that bond. So let's look at potassium iodide. When potassium and iodine atoms first come into contact with each other, before they are ions, when they're just atoms, then you're going to see a transfer of electrons. In this case, with potassium and iodine, which one is going to give up its electron, the potassium or the iodine? Potassium. So potassium is going to become positively charged, so it's going to give up its electron, and iodine is going to absorb that electron. Now, if we imagine these processes taking place step by step, we can show this using those Lewis dots that we just looked at. So for example, first of all, potassium will lose its electron and become potassium plus. Now here's the electron it lost. Iodine will then gain that electron, so that's the electron right there, will then go into iodine, making iodide ion or I minus. Now we have a positive potassium ion and a negative iodine atom. Now these two processes we learned about in chapter 7, and we learned about the energies associated with it. So what was the energy that is required to remove an electron and make a positive ion called in Chapter 7?
The electron affinity.
Ionization energy, good. So the ionization energy, I'll just put an IE, ionization energy was the energy that it takes to remove an electron. What was the energy it requires, or energy released when an electron is added called? Electron affinity. Good. So this one would have an electron affinity. So both of these processes would have energies associated with them. And where can we find these ionization energies and electron affinities? There was a table back, there were two tables back in Chapter 7, table for ionization energies and table for electron affinities. So if I go back and look at that, here's the ionization energy of potassium from that table in Chapter 7, and the electron affinity for iodine back in Chapter 7. Now, why is the electron affinity shown with a negative? Is it absorbing energy or releasing energy? Electron affinity.
Electron affinity is the value at which it takes to add an electron. So if that's a negative, then I think it's releasing energy, right? That electron is
Yes.
leaving.
Mm-hmm. No, for electron affinity, the electron's being added.
Right,
Yep,
right. But I'm
yep.
saying if that value is of a negative, then it's
The energy is
yeah.
leaving, yeah. So back in Chapter 5, we learned that enthalpy values, energy values, for exothermic reactions where the energy is leaving or being released are negative. So that's why it's negative, is because this is the energy that is being released when you add an electron to iodine. So you're releasing this energy. Now, if we take these two processes and put them together and find what is the energy of this process, it'll just be the ionization energy of the potassium plus the electron affinity of the iodide to do both processes together. When we do that, we end up with positive 124 kilojoules. Now, the problem is that means overall the process requires energy. So in order to make an ionic compound, it should require energy. We agree with that? According to this math. The problem is, when we actually form ionic bonds, it's a highly exothermic process. Why on earth is it highly exothermic if, according to our calculations, it actually requires energy? So one of the classic examples of forming an ionic bond that you may be familiar with seeing this reaction is to take pure sodium and drop it in water and make sodium hydroxide, which is an ionic compound. That process, does that give off heat or absorb heat? Just a little bit. Gives off a lot of heat, right? We've all seen the videos, at least, of taking blocks of sodium and dropping them in water. What happens? Yep, it blows up. Well, what's really happening is it releases hydrogen gas, and it's also extremely exothermic, so what happens to hydrogen when you heat it up a lot?
Expands. But then it also explodes.
Yeah, expands and then explodes. Yes, so hydrogen gas is extremely combustible, and so that's what we see, the lovely fireworks when we drop sodium into water. So that's an extremely exothermic process making that ionic compound, and all ionic compounds are going to be exothermic when they're being formed. So there's something else going on here than just ionizing the two ions and then bringing them together. So we're going to quantify these energy changes using something called the lattice energy. Lattice energy. So the lattice energy is the amount of energy that would be required to convert 1 mole of an ionic compound into its individual ions in the gas phase. In other words, how much energy does it take to break apart an ionic compound? So for table salt sodium chloride, it's a solid starting and an ionic compound. How much energy would it take to break it apart to sodium ions and chloride ions in the gas phase? Or in our potassium iodide example here, how much energy it would take to take this potassium iodide and put it into potassium ions and iodide ions, and it has a delta H value of 632 kilojoules per mole, which means if I reverse this process, go from the ions back to the ionic compound or forming the ionic compound, it would be negative 632 kilojoules, which is exothermic, releasing energy. So forming ionic compounds is exothermic, it releases energy. So where does this come from? And what does this tell us? Here on page 328, we have a table of lattice energies of common ionic compounds. So when I ask you questions, it might be one of these ionic compounds, it might not. So we are going to have to learn how to estimate the lattice energy and calculate the lattice energy. So the more energy it takes to break apart an ionic compound, the more stable the ionic compound is, the harder it is to break apart. So the higher the lattice energy, that means the more stable your compound is. So looking at these numbers here, there's our potassium iodide with the 632. We also here have sodium chloride with 787. So sodium chloride then would be what, harder or easier to break apart than potassium iodide? Harder, slightly harder. Takes a little bit more energy than take apart. And we can see this by looking at also the melting point. So the melting point over potassium iodide is 680 degrees Celsius, while sodium chloride is 801 degrees Celsius. So it takes more energy to break apart those ions. Although melting doesn't go all the way into the gas phase, of course, because that's vaporization, it does show us pulling apart the ions because in the liquid phase, they have freedom of movement to slide past each other. So we do have to at least overcome those electrostatic attraction, the ionic bonds. So notice some of these have much, much bigger numbers. Here's magnesium oxide, 3,890. It is extremely stable. It takes a whole lot more energy to break apart magnesium oxide than it does to break apart either sodium chloride or potassium iodide. And we're going to see in a little bit why that is. So let's look at 3 different iodide-containing ionic compounds and compare their lattice energies. So we have lithium iodide, sodium iodide, and potassium iodide. The reason we're comparing this is because the only thing that is changing is our cation, the positive ion. And what do lithium, sodium, potassium all have in common? They're all group 1A, which means they're all going to have the same charge. They're all going to become +1 ions. So in this case, when we're comparing it, all of them have the same charge. Now what I have down here, this right here, that is Coulomb's law. Coulomb's law says that the force of electrostatic attraction is proportional to the product of the charges, Q1 times Q2, divided by the distance between them squared. That is Coulomb's law, which is basically the same concept that we had in chapter 5 when we talked about the electrostatic energy. The electrostatic energy is proportional to the product of the charges, Q1 times Q2, divided by the distance. So Coulomb's law just puts it in terms of force and squares the distance, but when you're comparing two things and they both have the distances squared, it's going to end up being the same thing. So really, you can use either equation, it'll just work the same. So we know what Q1 and Q2 are. Those are just the charges on the ions. And we've known what the charges on a group 1A metal is, always 1 plus, and then iodide is a halogen, group 7, so it's going to be 1 minus, so that's always going to be +1 and -1. But the distance between them, to find the distance between these things, we're talking about the distance from the center of one to the center of the other. So the center of this lithium to the center of the iodide. To find that distance, what we're going to do is we're going to add up the radius of these two ions. So back in chapter 7, we had a table of ionic radii. So that was on page 303. So on page 303, it shows that the ionic radius for lithium is 76 picometers. Now, 76 picometers. A picometer is 10 to the -10 meters per picometer. They give this kind of funny looking thing, A with a little halo over top. That's called an angstrom. An angstrom is 10 to the -10 meters. Is an angstrom. So, sorry. I wrote that wrong. That should be 12. Right there. I was thinking a step ahead. A picometer is 10 to the -12 meters. Thinking one step ahead. Which means that there are how many picometers in a meter?
Billion?
What's the difference between 10 to the -12 and 10 to the -10?
A trillion? Is it a trillion?
How many picometers in one, okay, how many picometers in an angstrom? Let's do that one. Between picometers and angstroms. Picometers to angstroms. What's the difference between 10 to the negative 12 and 10 to the negative 10? 10 squared. So 10 squared, also known as 100. So are there 100 picometers per angstrom or 100 angstroms per picometer?
100 picometers per angstrom.
Good. 100 picometers per 1 angstrom. Therefore, if I have 76 picometers, that is how many angstroms?
That is 0.7.
Good. 0.76 angstroms. So that is where this number right here came from, 0.76 angstroms. So they're just the numbers from the table in Chapter 7. We've just converted the unit from picometers to angstroms. All right. Now, same thing for iodide. Notice as we go down the family, so lithium to sodium to potassium, what is happening to the ionic radius of our cation as we go down the family? It's increasing. So, Chapter 7, does it make sense that as you go down a family, your radius gets bigger? Yes, that is the trend we learned. Why does it get bigger as you go down a family? Not just adding another orbital, but adding another what? Not even just a subshell, but a shell. Okay, adding a whole other shell every time you drop down a period. So as you're going down the family, the size is increasing. As you increase the size, what does that do to the distance between the ions? Increases it or decreases it? Increases it. The sizes are getting bigger, so they're getting what? Closer together, further apart? Further apart. So as things get further apart, what happens to the attractive force between it? Does it get weaker or stronger? Weaker, right? Think of magnets. The further apart you pull magnets, the weaker you feel the attractive force between them. Same thing here. So as I'm getting, the distance is increasing, this proportionality is decreasing, and sure enough, the lattice energy is also getting smaller. So we can summarize this. Some of these questions are just going to be comparing. Which one would have the biggest lattice energy and why? If what you're comparing is going to be in the same family, meaning the charges are the same, you're going to be comparing the distances. The larger the ions, the farther apart the distance, the smaller the lattice energy. So I'll summarize that down here. Bigger ions equals smaller lattice energy. And that is because bigger ions are further apart. So the electrostatic force of attraction is weaker. Make sense? All right. Now let's change, instead of changing the size, let's change the charges. So we're comparing here lithium fluoride and magnesium oxide. If we add up the ionic radii of these two things, we get that both of them are pretty close to the same radius. So lithium is 0.76 versus magnesium 0.72, but fluoride 1.33, oxide 1.4. When you add those up, the distance here is going to be similar. So we're not really going to be able to compare distances here. But what we can compare is what is a big difference between lithium fluoride and magnesium oxide. The charges, good. In lithium fluoride, they are +1 and -1, while in magnesium oxide, they're +2 and -2. Which one will give us a larger magnitude of force? Magnesium oxide or lithium fluoride? Magnesium oxide gives us a larger magnitude of force. Now, I'm saying magnitude because you're always going to end up with the negative, but we don't really care about that. We're just looking at the magnitude. It'll always give you a negative because you're always going to have a negative ion on top. So the magnitude of force is greater. What does that mean about the lattice energy? If my force is greater, will my lattice energy be greater or smaller? Also greater. And sure enough, if I measure the lattice energy for lithium fluoride, it's 1,017 versus magnesium oxide. Was that a big jump or a little jump? Yeah, almost 4 times as big. That's a big jump compared to when we were just changing the sizes, where those big jumps are little jumps relative. Small jumps, little jumps. So which one do you think has a bigger impact on the lattice energy? The magnitude of the charges or the size of the ions? Magnitude of charges. So magnitude of charges has a greater impact on lattice energy. For that reason, if I'm asking you to compare lattice energies, always check the charges first, because if the charges are different, that's going to be significantly more important than the size of the ions. If the charges are the same, then you look at the size of the ions. So bigger charges equals bigger lattice energy. Make sense? All right, so let's try this out. Arrange magnesium oxide, calcium oxide, and strontium oxide in order of increasing lattice energy. So increasing meaning from smallest to biggest. Biggest lattice energy. LE. I'm just putting LE for lattice energy. Magnesium oxide, calcium oxide, and strontium oxide. So in this case, are the charges different, or am I going to compare the sizes? The sizes, because all of these have the same charges. Magnesium, calcium, and strontium are all plus what? +2, and then they all have oxygen. So what we're really comparing here is the difference between magnesium, calcium, and strontium. All right, magnesium, calcium, and strontium. If we're comparing the sizes, which one of these is the smallest ionic radius? And how can I tell without looking back at that table in Chapter 7? Magnesium, because it's the highest in the family of that group. So magnesium has the smallest ionic radius because it's the highest up in that family. Ionic radius. If it has the smallest ionic radius, what does that mean about its lattice energy? Good, it'll be the biggest, the highest lattice energy. So magnesium oxide will be my biggest lattice energy. What will be my smallest lattice energy? Strontium, good, because strontium of these three is the largest ionic radius, which means that it is the furthest away from oxygen of that group. So that would be the smallest lattice energy. And then we'll put calcium oxide in the middle here. Any questions about how to apply those? So did we actually have to calculate the lattice energy to answer this question? No, we were just comparing. Just like in Chapter 5 when we were comparing electrostatic energies and I just asked you which one has the greatest electrostatic energy, all you were doing was comparing. You didn't have to actually calculate the electrostatic energy. Same here. You didn't. If I'm just asking you to compare which one's biggest or put it in order of increasing or decreasing, you don't actually have to calculate the energy. And the reason why I say that is that the method of calculating the lattice energy is kind of involved. So if you can avoid doing it, it'll be, helpful to not go through the process. We good with this one? Ready to talk about how we actually calculate the lattice energy? All right. So we're actually going to calculate the energy using something called the Born-Haber cycle. So if you're following along in the textbook, we are on page 330, although on page 332, 333 is this nice 2-page spread showing all of the steps of the Born-Haber cycle. And there are 5 steps. So, Hess's law in Chapter 5 tells us that the total enthalpy of a reaction can be equal to the sum of the enthalpies of the individual steps. So back in Chapter 5, we had multiple reactions, and we lined them up and added up their enthalpy values to find the enthalpy of the overall reaction. That's what we're going to do here. We're going to find the enthalpy of each of the 5 steps and then just add them up, and that will be our lattice energy. So what are those 5 steps? Again, lattice energy is how much energy it takes to go from a solid ionic compound to the individual ions in the gas phase. So this is going to take 5 steps. Each of those steps is going to have an energy associated with it. So the very first step is going to be to take this ionic compound and break it apart into its 2 separate elements in their standard states. Now, let's look about what the reverse is. What is taking elements in their standard states and turning it into a compound? What is the energy that is associated with making a compound out of its elements in their standard states called? Back from chapter 5. The enthalpy of what? Formation. The enthalpy of formation. So the symbol for enthalpy of formation was delta HF. And then the little degree up there means standard state. Where do we find enthalpies of formation? Where do we find them back in chapter 5? It was a big table, really big table. Where was it in your book? Very back of the book, right? The appendix. So standard enthalpy of formation, these values are found in the back of the book. So that's from the appendix 2. Appendix 2. Now, why did I make it negative? Why did I change the sign? Because we're going backwards. Instead of forming the compound, we're breaking it apart. Because we're doing the reverse reaction, we learned also with Hess's law, if you reverse a reaction, you change the sign of your enthalpy term. So that's why I took that value and I made it negative. So that is the step 1. Step 1 is going to be the opposite of the standard enthalpy of formation for whatever your compound is. And that now gets us to where our compound is separate into its individual elements. Step 2. Now, according to the definition of lattice energy, what phase must these ions be in? Gas phase. The problem is the standard state of metals is not a gas phase. None of our metals standard state are gas phase. So we're also going to need to take those and put them into the gas state. Now, when we were learning about standard enthalpy of formation, the standard enthalpy of formation for an element is 0 if it is in its standard state. If it's in any other state or another state of matter, it will not be 0. So second step, step 2, is we're going to take our metal and go from the solid state to the gas state. And again, that is going to be a standard enthalpy of formation because that is not the standard state for that element to be a gas. It's going to take energy to do that. And again, we find that value in the appendix. The next thing we're going to do is for most of these ionic compounds, we're going to be dealing with a nonmetal that happens to be, its standard state is a diatomic. So all of the halogens, group 7A, including our chlorine here, are always diatomics, meaning that their standard state is not just Cl, it's Cl2. Before we can become an ion, though, we need that to just be a single atom. So we need to take our anion and go to a single atom just in its atomic form. Again, because that's not a standard state, there's going to be a standard enthalpy of formation for that. And again, we can find that in Appendix 2. So there's our third step. Step 3, take our nonmetal, go into the atomic form. So those first 3 values we can get from the appendix. 3 down, 2 steps to go. So now we have our 2 elements as single atoms in the gas state, but we need them as ions. So the next 2 steps are going to be turning those into ions. So first, let's turn the metal into an ion. So to have sodium go to sodium plus, that's losing an electron. What's the energy associated with losing an electron called? Ionization energy. Good. So there's the ionization energy of sodium. Where do we find that value from? Where was the table for ionization energies? Good, in chapter 7. So in chapter 7, there was a table of ionization energies. Next one, making chlorine here going to become chloride ion is adding an electron. What is the energy associated with adding an electron called? Electron affinity. So step 5 here is going to be the electron affinity. Now, why did I make it negative? If I go to chapter 7 and I look at the electron affinity values, with the exception of our noble gases, nitrogen, they're all positive. But electron affinity, by definition, is energy that is being what? Released or absorbed? Released, because that table of electron affinities is giving us the amount of energy. That's why it doesn't include the negatives. But we know this is energy being released, so we need to make that negative because that energy is being released. And again, we'll get this from a table in Chapter 7. Add all these 5 steps up, and you will get the overall lattice energy. LE lattice energy is equal to the sum of these 5 steps. So there's step 1, step 2, step 3, and then step 4 and 5. Again, the first 3 steps, you can get those values from Appendix 2. And then the last 2 steps you can get from Chapter 7. Starting to see why, if you can get away with just comparing the ion size, it's probably preferred than actually calculating out the lattice energy, if you can avoid it.
So just looking at those tables from Chapter 7, in step 4 and 5?
Yep, 4 and 5 are from the table. So this is for sodium chloride. Let's find them. So the standard enthalpy of formation of sodium chloride from Appendix 2 is 410.9. These are all in kilojoules per mole. Standard enthalpy of formation of sodium in the gas phase is 107.7 kilojoules per mole. Standard enthalpy of formation of chlorine atoms in the gas phase is 121.7 kilojoules per mole. And then the ionization energy of sodium from Chapter 7 here is 495.5, or sorry, per 9 kilojoules per mole. And then making it negative, the electron affinity of chlorine from Chapter 7 is 349 kilojoules per mole. Add all of these up, and you should get 787 kilojoules per mole. And this is the lattice energy for sodium chloride. And again, that's from the 2-page spread on page 332, 333. Nice, color-coded, and each of the steps is also color-coded. So you can see, oh, here's the yellow step. That's the value to go with the yellow step. Try to keep track of where these numbers come from. All right, ready to try this out? It's not hard, you're just adding 5 numbers. It's just tedious because you have to look up those 5 numbers, right? That's the tedious part. All right. Using data from figures 7.8 and 7.10, so those are our ionization energies and electron affinity tables back from Chapter 7, and Appendix 2, so those are standard enthalpies of formation there. Calculate the lattice energy of cesium chloride. Cesium chloride. So, in the interest of saving time, let's go ahead and I'll just give you the values from those tables. So the very first thing that we need is the standard enthalpy of formation for cesium chloride. Where is it? Standard enthalpy of formation for cesium chloride is negative 442.8. But we're going to put a negative in front. Why do we put a negative in front of the delta H formation for the compound? Why did we do that here? Why do we make it negative?
Because it's going in reverse.
It's going in reverse. Instead of forming the compound, we are breaking the compound apart. So if I look in the Appendix 2 and I see that cesium chloride is negative 442.8, I'm going to make a negative of that, negative, negative, and that becomes positive. So that is the standard enthalpy of formation for cesium chloride. All right, so that's step 1. Step 2 is the standard enthalpy of formation for the metal in the gas phase. So now we want cesium to be a gas. So the standard enthalpy of formation of cesium in the gas phase, 76.50 kilojoules per mole. Kilojoules per mole. So that was step 2. Step 3, we need the standard enthalpy of formation for our nonmetal, which is chlorine, to just be one atom instead of the diatomic. So that was for chlorine, that was 121.7? Yeah, 121.7. 3 steps down. Next, the ionization energy of the sodium ion. For the sodium ion from chapter 7.
Everything listed on the next slide.
Oh, well. We're already this far. 376. And there's step 4. And then step 5.
For cesium or sodium?
Cesium.
You wrote sodium.
I did? Yeah, I did. You're right. That should be cesium. CS. So and then the last step is the electron affinity of our negative ion, which is chlorine, making it negative because it is the energy being released. So step 5 is the electron affinity of chlorine, which is 349. Add all of those up and we get what?
668.
Good, 668 kilojoules per mole. Woo. So 5 steps, but again, the tedious part is looking up the values from the table.
Is the last step the only one you subtract because it's negative?
The first step and the last step. First step and the last step are both subtractions. Everything else is plus.
Wait, the first one's saying you subtract the negative values.
In that case, it was a negative value. It might not always be. I don't think it was with sodium chloride, was it? Yeah, with sodium chloride, it was a positive value.
Just follow the formula.
So you're just following these steps here. It is the negative delta H of formation for the compound, plus the delta H of formation for the gas phase of the metal, plus the delta H of formation of the single atom for our nonmetal, plus the ionization energy of our metal, minus the electron affinity of our nonmetal. 5 steps. I did not give you one of those in the homework, but you will probably see it on the Learn Smart, just because I don't control what Learn Smart throws at you. Any questions about ionic bonding before we're ready to spend the rest of the chapter on covalent bonding? Covalent bonds. Yay!
Does ionic bonding only occur with alkaline earths and the other gases are like?
No, they occur with everything else, but we're only going to focus on those that are the alkaline earth metals and aluminum, because or the alkaline metals, alkali earth metals, and aluminum, because those have definite charges. So.
Aluminum has like only +3 charges?
Yes. Yep. Aluminum's only +3. All right. Covalent bonding. So There are different theories of bonding, and we're going to start with the simplest, easiest to follow bond theory and then work our way up through the end of chapter 9 with the more complicated, a little bit more effort required bonding theories. So the simplest and easy theory of bonding, or the most commonly used still because of how quick and easy it is called the Lewis theory of bonding, and it is based on Lewis dot structures. So the simplest form of the Lewis theory of bonding, I call this the connect the dot theory of bonding, because you're going to start with Lewis dot theory, and then you're just going to connect the dots, pretty much. All right, so for example, let's look at forming the hydrogen bond in H2, or the hydrogen-hydrogen bond in H2. So each hydrogen has one dot because they each have one valence electron. To show the bond formed here, we are going to connect the dot from a single dot to another single dot. And here's what we end up with. Now, what happens here really is that these two electrons come closer and closer to each other because this hydrogen over here sees that electron. Now, hydrogen has one electron, but how many does it really want? Two, because everybody wants to look like noble gases. What's the nearest noble gas to hydrogen? Helium. Helium has how many electrons? Two. So hydrogen really wants two electrons, but he's only got one. But he sees this other electron over here, and he's going to reach out and grab it and start pulling it towards himself. But at the same time, this hydrogen over here sees that electron and starts pulling on it. So unlike an ionic bond where the electron is transferred, they're going to pull on each other until they come close enough to each other that both hydrogens are kind of tricked into thinking that they now have two electrons. But the truth is they're sharing the electrons. They both think, hey, I've got two electrons, I look like helium, everything's good. But those two electrons are actually being shared between the two atoms. This is called covalent bonding because the electrons are shared, not transferred. Now, these covalent bonds, compared to an ionic bond, do you think this is weaker or stronger? An ionic bond is the electron gets transferred, and then what holds it together is just electrostatic force. One thing's positive, one thing's negative. It's like magnets. Whereas here, I'm sharing electrons. Which one do you think is going to be harder to break? Shared electrons or just attractive forces because they're oppositely charged? Shared. So covalent bonds are significantly stronger than ionic bonds. Ionic bonds, again, we think of that like magnets. They're oppositely charged, so they're attracted to each other. Covalent bonds, now that we're sharing it, this is superglue. A lot harder to break. So sharing electrons makes a much stronger bond. So think sharing things makes a stronger bond. I try and convince my kids that when they're fighting with their siblings, and they say, but I don't want to be bonded to him. Yeah. Oh, my poor kids. They get everything with a chemistry analogy. Fine, we'll stop fighting. Just stop talking about chemistry, Mom. So here's fluorine. Now, fluorine has how many electrons? Valence electrons? 7. So if I draw the Lewis dot structure of fluorine, I have 7 electrons. What we have here is an unpaired electron. Unpaired. Unpaired electron. In the Lewis theory of bonding, only unpaired electrons are available for bonding. They're the only ones that can be shared. So again, when I say connect the dots, I mean from an unpaired electron to another unpaired electron. You cannot connect dots that are already paired. Back to the idea of orbitals, you can only fit 2 electrons in an orbital, you can only fit 2 electrons in a bond. So each time we draw one of those lines, it can only hold 2 electrons, therefore it can only be from an unpaired electron to an unpaired electron. So based on this idea, looking at the Lewis dot structure of fluorine, how many bonds can fluorine make? Just one, because it only has one unpaired electron. How many bonds can hydrogen make? Just one, because it only has one unpaired electron. So this is also going to start explaining how many bonds things can have. So the unpaired electrons versus the ones that are already paired are called lone pairs. Already paired electrons are called lone pairs. And again, we're going to connect the dots from unpaired electron to unpaired electron, and that is where we get this structure. Now, in this case now, each fluorine thinks they have a total of 8 electrons, or 8 valence electrons. So each one of them now feels like a noble gas, even though they're technically sharing them. Yes?
Atoms that are bonded together like that versus diatomic atoms.
This is a diatomic molecule. This is F2. F2 is a diatomic molecule, meaning it's a molecule made of 2 atoms.
But
What do you mean?
it's not I thought it wasn't only the halogens that could be, it was Han and the halogens.
Han and the halogen. So hydrogen, oxygen, nitrogen, and then everything in group 7 does this.
So those are the only ones that are covalent bonds?
No, you can also have covalent bond through things. So these 2 examples we've done so far, these are homonuclear, meaning that they're the same atom. You can also have heteronuclear bonds. So let's look at a heteronuclear bond. So let's see. Here's some heteronuclear bonds. Actually, let me do in this space where we have right here. Let's do the hydrogen to fluorine. So hydrogen versus fluorine. Yeah, well, hydrogen fluoride in gas phase, hydrofluoric acid is a liquid. If I wanted to show the bond between here, again, I'm going to connect the dots from unpaired electron to unpaired electron. So from this unpaired electron to that unpaired electron, I will connect the dot there. So the resulting structure is going to have, can't draw here, hydrogen bonded to fluorine, and then what else is fluorine going to have? 6 unbonded electrons or 3 lone pairs. So there's my Lewis dot structure for hydrogen fluoride. Let's look at oxygen. How many valence electrons does oxygen have? 6, good. 1, 2, 3, 4, 5, 6. How many bonds can oxygen make? 2, because I've got 2 unpaired electrons. I can't bond to the lone pairs. These are set, so I can only make 2 bonds there. So I can come in with 2 hydrogen atoms here and make a bond with a hydrogen on one side, make a bond with a hydrogen on another side. And I've just made what molecule? Water, right?
So, why does water have that angle between sides?
Good question. And we'll cover that in the beginning of chapter 9 when we do Vesper theory. Why it ends up being, instead of being a linear molecule, why does it end up being bent? But the idea behind it is because those lone pairs line up on one side and they're pushing the bonds away from them, and that squeezes the bond angles closer to each other. All right. You can also have multiple bonds. For example, let's look at our oxygen again. Oxygen, again, has 1, 2, 3, 4, and I'm going to line it up this way. 6 electrons. If I have another oxygen nearby, and they're going to bond with each other, how many places can these 2 oxygen atoms bond to each other? In 2 places, because they each have 2 unpaired electrons. So when they bond, what's going to end up happening here is they will form 2 bonds between each other. And then each one of them also will have 2 lone pairs of electrons. I'm just going to draw them over there. And I've just formed a double bond. So a single bond is where a single pair of electrons is shared. A double bond is where 2 pairs of electrons are shared. So what do you think it happens, what we call it, when 3 pairs of electrons are shared? A triple bond. Good guess.
Are they stronger than a single bond?
Yes, because you have to break more bonds. Each time you add another bond, it gets stronger. So here's some examples of double bonds. We have the double bonds between carbon and oxygen in a carbon dioxide molecule. By the way, carbon, how many valence electrons are around carbon? 4. So how many bonds can carbon make? 4. It makes 4 bonds, which makes it a perfect center for molecules because it can make so many bonds, which is why We build an entire branch of chemistry based off of molecules with carbon at the center. What is that branch of chemistry called? Organic chemistry, right? Organic chemistry, because these are the molecules that build up organic things, including yourselves, organic molecules, organic based compounds. Oh. All right, so we can make 4 bonds to carbon. So each oxygen can make 2 bonds, each carbon can make 4 bonds. So looking at the carbon dioxide molecule, this carbon in the center has a total of 1, 2, 3, 4 bonds. Each oxygen has a total of 2 bonds. See where we're going here? Draw the Lewis dot structure of the atom, and that will tell you how many bonds you are making. Double check to make sure everything has an octet, meaning everything has access to 8 electrons. There will be some exceptions to that. I mean, obviously hydrogen only wants 2, but triple bonds, such as the triple bond between 2 nitrogens. Each nitrogen has how many valence electrons? 5, good. Which means each nitrogen can make how many bonds? 3. 1, 2, 3 unpaired electrons, so each nitrogen can make 3 bonds. So if I put 2 nitrogens up close to each other, they are going to want to make 1, 2, 3 bonds with each other, or a triple bond, end to end. You can also make triple bonds between 2 carbons.
Is that why nitrogen is so good?
Yes, because the triple bond is extremely strong. Multiple bonds are much, much stronger than single bonds. The more electrons you're sharing, the closer you come together, the more that you have to break apart. Back to the old fable of if you take one stick and break it, it's easy, but if you take multiple sticks together and try to break it at once, it's very hard to break. Same idea with bonds. Single bond, you snap it. Put 3 of these sticks together, it's a whole lot harder to break. That's why nitrogen triple bonds, very, very difficult to break, and nitrogen in general is an inert molecule. You have to really push the reaction conditions to force it to react. So looking at those bond lengths, this is going into the idea of strength. Bond length is going to be defined as the distance from the center of one atom to the center of the other atom. So with ionic bonds, it was just the sum of the ionic radius of the 2 ions. But with covalent bonds, because they're sharing electrons, they're going to overlap. So the bond length is going to become closer together and get shorter. So here we have nitrogen N2, our triple bond, and then carbon monoxide, also going to be a triple bond there. And we're going to overlap these things so they come closer and closer together and get relatively small bond lengths here. So 1.10 angstroms on the nitrogen versus carbon monoxide, 1.13 angstroms. In general, if we look at the same 2 atoms being bonded together, so let's look at carbon to oxygen, single, double versus triple bond, what is happening to your bond length as you make more bonds? It's decreasing. So the more bonds, the closer you get together. Again, sharing more brings you closer together. But Mom, I don't want to get closer to him. He's a boy. He's gross. Same thing with nitrogen to nitrogen. As you get more and more bonds and you're sharing more, your bond length decreases. You get closer together and you make a stronger, harder to break bond.
Where does a single bond normally occur with nitrogen?
It's if on either side, it had the other things bonded to each other. Yeah. All right. So what is holding these things together? In Chem 152, the first chapter we start off with, chapter 11, is going to be intermolecular forces. So intermolecular forces are the forces between separate molecules. Intramolecular forces are the forces within the molecule. So when we're talking about bonding, in chapters 8 and 9 right now, bondings are intramolecular forces. They are holding together the molecule. Intermolecular forces between molecules, we'll spend all of chapter 11 on that in Chem 152. But just so if you see those terms, you know what they mean. In general, intermolecular forces are relatively weak compared to intramolecular forces. It takes a lot more energy if I'm looking at, for example, H2O, hydrogen. So if I have two water molecules sitting around next to each other, the intermolecular force is the force that holds these two molecules together in, say, the solid or the liquid phase. Whereas the intramolecular force is the force holding the hydrogen to the oxygen. Which sounds easier to do? Pull two water molecules apart or pull the hydrogens off of an oxygen? Which is harder, pulling the hydrogens off of the oxygen or just pulling two water molecules apart?
Pulling two water molecules.
Which one's harder?
Oh, okay.
Pulling the hydrogens off of the oxygen is going to be a whole lot harder. So intermolecular forces are generally the weaker forces. It's easier to pull apart molecules than it is to pull the molecules apart. Does that make sense? That does make sense. All right. So in general, things that are covalent tend to have relatively low melting points. For example, water has a relatively low melting point. What is the melting point of water?
100 C.
Melting point.
0 C.
0 C. So relatively low melting point. All right. So we are, on the other hand, in an ionic compound, we learned back in chapter 2, they form large three-dimensional structures. So the three-dimensional structure is held together not by an intermolecular interaction, but by the intramolecular interaction. So to take a block of solid sodium chloride and melt it, we're not overcoming intermolecular forces, we're overcoming the ionic bonds themselves. So which would have a higher melting point, a covalent compound like water or an ionic compound like salt? Ionic compound like salt. So, all right. So we're going to stop there and pick up this on Thursday.